All right. Welcome to the MAS 575 Combinatorics. So in the beginning of this course, I'm going to show you some sample list of theorems, which shows you various methods that are going to be covered in this class. So the first example is this even-odd rules for clubs. So let me tell you some artificial story. So in our university, there are many student clubs. And the president may worry that there are too many student clubs. So in order to limit the number of student clubs, one day the president made an artificial rule. So that's one of the name of this rule is called even rule. The goal is to limit the number of student clubs, right? So the even rule, what are the even rules? Every student club has even number of students. So the student club having odd number of students is forbidden. Second rule is every pair of clubs must share even number of students. And the third rule is that no two clubs are identical. So what does that mean? Well, if I say A1, A2, AM be the sets, right? Subsets of 1 up to n, and the even rule. So think of n as the number of students, and AI is the set of students belonging to the i's student club, right? So the first condition says that AI is even for all I. And the second condition says that when you have two distinct clubs, their intersection is even for all I and j. And third condition says that AIs are distinct. So question, what is the question? So the goal of this rule was to limit the number of possible student clubs. So how many student clubs can student form? Right. So you cannot have a 2 to the n student clubs because 2 to the n is the number of subsets of n set, and among them there are subsets of size odd, right? So that's forbidden. And it turns out that, okay, you can think about it. So here's one solution, right? So partition the students into sets of size 2. Maybe the last one only has 1. All right, and then, so for each pair, each student club either contain both of them or none of them. All right, so in other words, you just take the all possible subsets of these pairs, and number of pairs is n over 2. Let's take a floor. So you can have so it's possible to create like 2 to the n over 2 clubs following the odd rule, no even rule, right? So still the president may think that you can make too many student clubs. So one day he came back and say, oh, okay, so you can make too many student clubs. Let's make a different rule. Instead of having even rule, now we're gonna modify the rule, and the new rule is called the odd rule. Okay, so what's the new rule? Well, only one changes. Every student club must have odd number of students. For any pair, the intersection is even. If that's the case, no two clubs will be identical, so I can safely eliminate the last condition, right? Because if two sets are same, their intersection has to have same odd size, which is not the case. All right, now, so another way of saying is, same situation is you have a list of subsets such that each AI is odd and AI intersection AJ is even. So how big can M be, right? How can I increase M as big as possible? So what are the examples? So in the previous situation when we had the even rule, you could make 2 to the n over 2 distinct clubs. So here, well, so for instance, you can make n clubs easily, right? How? Well, AI is just a club with a ith student, right? So you have n distinct clubs. Each AI has size 1, and no two AI, I mean, whenever you have AI n and j, their intersection is empty, which is 0. So that's one example. There are many other examples. For instance, I can take I can probably start with the identity matrix, all right? And then so let me write this way. So here's A plus I, and A plus I. Oh, all right. Let me just skip. Doesn't matter, right? So this is an example, but it's not unique. All right. Okay. I wanted to show you why it's not unique. So for instance, I will give you some example. Okay, so 0 0 0 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. So what's this formulations? So these rows correspond to students and columns correspond to the clubs. Okay. Now, if an entry is 1, that means a student belongs to the club. Entry is 0, then student doesn't belong to the club. All right. And now, if you look at each column, then you have exactly odd number of ones. All right. And if you look at the 2 distinct columns, their intersection is even. Why? Well, you can check it. One answer is you can check it, and another answer is the formulation is made from this configuration. So A plus I, A plus I. If I take 2, and A is symmetric, let's say it's n over 2 by n over 2, 0, 1 matrix, right? If I take two columns, right, it's possible that I may take two columns from here. Then the intersection here and intersection there will have the same parity, right? Because here the intersection, I mean, the thing is, if I take two people on the same side, like i's and j, and then here you have i's, j, and I and j, right? And because we are adding identity matrix over this part, so these red parts and these blue parts, the answer will be the exactly opposite, right? So if the red part coincide, is both sides are 1, then the blue part you will have a different, and they will be different, right? So because one here you're adding 1, here you're adding 1. So these red and blue are the only places where top and bottom could be different. All other places, if it's same on the top, then it's same on the bottom, right? If these two are same, then these two are same. These two are different, then these two are different. So everything else cancel each other. So we only care about the number of places where they are equal, right? So if these are equal, they are equal. So they come in pairs. But if they are different, then they are equal. If this is different, then they are equal. But the thing is, you have two places. So in the end, the number of intersections, I mean number of ones in the intersection is even when you take things from the same thing. If you take things from different column, you can still argue same way. So there are many n over 2 times n over 2 symmetric binary matrices. All of them generate one of these configurations. And yet, surprisingly, what we can prove is that the president is happy. Instead of allowing exponentially many distinct student clubs, now the students can only make n clubs. So here's the theorem. With n students, no more than n clubs can be formed under the odd rule. Well, let me say in other words, if A1, A2, AM are subsets of 1 to up to n, and each AI has odd size, AI intersection AJ is even for all I distinct from U. Then the number of such set is at most n. That's the theorem. So this huge difference, right? When you have even, then you could have 2 to the n over 2, but now you have only have n. So I'm going to show you two proofs. So both proofs will have applications with other combinatorial problems. Right? So the first proof, how do I do the first proof? So I will construct a vector. So it's vi1, vi2, vi(n). These are vectors in the binary vectors, the vectors n-dimensional vector space over the binary field. So F2 is filled with two elements, 0 and 1, right? So 1 plus 1 is 0. So vi, so for I 1 up to m, vi is this thing where vij is 1 if j is contained in ai and 0 otherwise. All right. Now let's look at the inner product between two vectors, vi.vj. What is vi.vj? That is, it's a sum over all k, right? vik and vjk, right? Now, vik, vjk, these are 0 or 1. So in order to have any survivor of these terms, you need to have both to be 1, right? So that means it's exactly the ai intersection aj, right? And this is 1 or 0 if I is different from j, and oh no, if I is equal to j, then it's odd. So everything, so this is a element of the field, right? So it's binary fields. I'm doing all the computation in modulo 2, all right? So if I is equal to j, then ai intersection aj is size of ai, and size of ai is odd, so it's 1, and otherwise it's 0. All right, now here's the claim. All these vectors are linearly independent. Okay, so now I should say it's linearly independent. Suppose not. Then there's a linear combination for some ci, right? But then ci vi dot vj is going to be ci vi dot vj, but this, what's going on? But this is going to be cj, right? Because when I is different from j, this will become 0. And I know that this is 0 anyway, so this means that cj is 0 for all j. So this proves that these vectors are linearly independent. But those vectors are, they belong to this n-dimensional vector space. Right? In an n-dimensional vector space, you cannot have a linearly independent vectors of size m. I mean, size too big, right? So any set of linearly independent vectors have size at most the dimension of the vector space. So m is at most n. Right? So that's the proof. So we're using elementary linear algebra to prove a fact on extremal set theory. So that's the first proof. I'm going to show you another proof as well, which is also based on the linear algebra. Right? So let's take M to be matrix V1, V2, Vm, where these Vi's are from the previous proof. So in other words, this is a matrix where the rows correspond to students and columns correspond to the clubs. And it's 0-1 matrix. So it's over, this is a matrix, be an m by n matrix over this field. Okay, now I'm going to consider this matrix A, which is m transpose times m. So the rows becomes clubs and students, and then students and clubs. So what is this matrix? Well, I take this column and multiply with that. That's gonna be the entry, right? But these are like V1 transpose, V2 transpose, and Vm transpose, and these are like V1 and Vm, right? So the each entry is going to be Vi transpose times Vj, right? That's going to be the entries, and rows are indexed by clubs. Columns are indexed by clubs. So what is this? This is nothing but Vi.Vj, and we know that this is exactly the identity matrix. So this is the M by M identity matrix. Now here's a key fact that we're going to use. When you have two matrices A and B, the rank of A times B is always less than or equal to the rank of B. This is an easy fact from the linear algebra. There are many ways to prove it. I'm not going to show you how to prove it, but you can easily prove it. So let's apply this. Rank of M transpose M is less than or equal to rank of M, right? Rank of M is less than or equal to the number of rows of M, which is equal to M. No, number of rows is number of students, it's N. And this is identity matrix, so this is M. So that means M is less than or equal to N. All right? So with this odd rule, the president is happy because students can only make N student clubs, no more. That's surprising, right? It's just with just a little bit of changes, you can make huge difference. So maximum number of distinct sets you can form is at most N. So later we're going to see many of these types of theorems. We will talk about the extrema set theory, where you have a list of sets satisfying certain conditions, and you want to find the maximum number of sets you can make. And in many cases, you're going to use linear algebra. Sometimes you use induction, and we will see many of the interesting methods to prove such a thing. All right, so now let's go back to the even rule. We've seen the example where you have exponentially many distinct clubs, 2 to the n over 2. Is this best possible? Is there a way to achieve a little bit more than that? And actually, no, this is best possible. With n students, no more than 2 to the n over 2 clubs can be formed under the even rule. In other words, if A1, A2, AM are subsets of 1 up to n, where H, AI is odd, AI intersection AJ is odd, no, not odd, even. And these sets are distinct, then the number of sets is at most 2 to the n over. So how can you prove a theorem like this? And again, we're going to use the linear algebra, right? What's going to show? I'm going to take Vi with the same thing. Right? So Vij is 1 or 0 if j is in AI and otherwise. Now, let U be the span of all these vectors. So it's a subspace of f2 to the n, right? And between each pair, each of them are orthogonal, right? So we know that vi dot vj is 0 for all I and j. So that means that for all x in U and for all x, y in U, their inner product is 0. Oh, I should use different notation for inner product. X dot y is 0. Right? Because between vi and vj, their inner product is 0. So any linear combination of vi will, like if you have a linear combination of vi, ci vi, that di vi, well, this will become 0, right? So x is spanned by them. So x is sum of ci vi and y is sum of di vi, but their inner product is going to be 0. So this means that U is actually contained in the orthogonal complement of U, right? So this notation means that it's a set of vectors where x dot y is 0 for all x in U. Okay. Now, why is this useful? Because here's one theorem in the linear algebra. Dimension of U plus dimension of orthogonal complement is equal to dimension of the whole space. This is true for any subspace. So now I know that this is twice dimension of U. I mean, twice dimension of U is a lower bound because U is contained in here, right? So dimension of U is less than or equal to half of the dimension of f2 to the n, which is half of n. Alright? So that means dimension of U is less than or equal to n over 2 floor. Now you have a subspace of n-dimensional vector space, which is of dimension n over 2 floor. So the number of vectors in U is at most 2 to the n over 2, because any vector is a linear combination of these n over 2 vectors, and the coefficients are 0 or 1 because it's binary field. And v1, v2, they belong to U, so that means m is at most 2 to the n over 2. All right, so that's the proof. So this is like linear algebraic method to prove that a certain set system cannot be too large. All right. Now let's move on to the next example in the next video.